Hello everyone, welcome to my channel. Today I'm going to talk about in detail how SQL Server utilizes memory. So firstly, why I created this session. Imagine your query started to run slowly. Then after checking, you found SQL Server is using 90% of the system memory. Then you started to suspect that this is a memory contention issue, but you are not sure. In this case, how do you start troubleshooting? How do you confirm whether this is a contention issue? Maybe this is expected behavior, right? Or imagine you started to see this kind of logs in SQL Server error log. What does this page out mean and why this might be happening? How to prevent this issue in the future? In all of these kind of memory related issues, first of all, we should understand how Windows and SQL Server interact and manage memory internally. In this session, firstly, I'm going to explain the fundamentals of how Windows manages memory. I did not go deep, I only explain related information, okay? Then I will focus on SQL Server's internal memory structures, how they are managed, and how you can break down them for effective troubleshooting. Let's get started. When the term physical memory is used, we understand the fastest type of storage hardware with limited size like 4 GB, 8 GB. Compared to disk, as we know, RAM is faster. So we prefer to work with RAM always. But we wish we could save all of our data in RAM. RAM is very much expensive compared to disk and limited with size. So therefore, we should use both of this hardware in our system by keeping balance. As a result, the concept of virtual memory and virtual memory manager came in. How does this structure work? Instead of physical memory, processes access virtual address in virtual memory. Then the request is directed to virtual memory manager, which holds the page table entries that map virtual addresses to physical address. However, mapping is not always done to physical memory. Since we have limited size in memory, when it becomes full, some data is moved to disk temporarily. We call this paging out, okay? This paged out data is also tracked by memory manager. If any process asks this paged out data, for example, virtual memory manager just brings this data back to memory and returns the data back to process from memory itself. We do not bring data directly from disk. We should first bring it to memory, then return it to the process. From this, we can conclude that virtual memory is just RAM plus paged out data in disk. In this way, we are able to increase our memory size without increasing costly physical memory. As you might have paid attention, paging out causes some latency, right? There is I/O latency, and we should also bring the data to memory, then to process. Therefore, when you have a lot of paging out and paging in process out there, you should troubleshoot and try to decrease this process. Now, for next part of the session, I want to take this whole part as just memory, whose size equal to virtual memory. In the next slides, when I speak memory, imagine this structure always. Let's concentrate on the connection between memory and process, this part. As you know, each process runs its tasks on CPU. CPU nowadays is divided into following structure. First, there is a socket. On sockets, there can be one or more cores. And each core can also consist of logical CPUs. Each CPU runs one task at a specific time. So we have 8 logical CPUs here, right? This means we can run 8 process tasks in parallel. Each task requires memory, of course. We cannot run the tasks without memory. So they will try to get memory, but they cannot do it directly. They will first connect to front side bus. Front side bus directs this request to memory controller, and final request reaches memory. Then memory is allocated to each task being run on CPU. This structure is very much conventional and was invented when there were very few CPUs. Nowadays, as CPUs are becoming very much strong and the number of them increasing per socket with many logical CPUs, the contention arises while accessing the memory. As you can see, each CPU is using one bus, right? If there is more and more CPUs added, there will be contention here. As a result, we can face latencies in accessing and allocating memory. To resolve this issue, NUMA concept has been created. NUMA system is hardware design, where system processors and memory is divided into groups we call NUMA nodes. Each processor has its own memory controller and direct connection to dedicated memory. We call this memory as local memory. In this case, when we submit tasks to CPU, memory is easily allocated from local memory and we don't face any latencies in memory allocation. At least less latency, okay? Let's now slowly switch to SQL Server memory architecture. For example, you have two NUMA nodes. When you start SQL Server automatically detects these NUMA nodes and creates its own NUMA architecture, parallel to this OS level architecture. As you can see, SQL Server creates schedulers parallel to each logical CPU. When SQL Server submits any query, the task is firstly submitted to scheduler. Scheduler then submits the task to NUMA node architecture it belongs. Okay? Of course, logical CPU needs memory to run this task, and it gets the memory from local memory without latency. We call this upper part as SQL OS. I don't want to speak much detail about SQL OS here. If you want to deeply learn SQL OS, please refer to my another video where I explain it very deeply. You might ask, what happens if we don't have any NUMA architecture at hardware level, right? In this case, SQL Server creates one soft NUMA node, 0, with parallel schedulers. As you can see, all these schedulers and CPU get memory from global memory, which might cause latency a little, right? You can check your NUMA configuration by going to SQL Server error log. As you can see, I have 32 logical processors, but I don't have NUMA configuration in my hardware level. Therefore, SQL Server created one soft NUMA node 0 and allocated all schedulers to this node 0. We can also run this OS schedulers query to check allocated schedulers. One scheduler is allocated for dedicated administrator DAG. Okay? You can also check the number of SQL OS NUMA nodes. You can see we have one node 0 and one node which belongs to DAG. SQL Server always keeps one DAG node. This is not so much important, so you can ignore this one. Now we understood the importance of local memory and how SQL Server accesses it, right? Let's now learn how SQL Server utilizes local memory efficiently. We are coming to interesting point. So until now, we learned that system memory consists of physical memory and pages on disk. We call it this as virtual memory. To quickly access this virtual memory, NUMA nodes are created by dividing this whole virtual memory into local memories. You know already. So schedulers utilize this local memory, right? Do you think scheduler can directly utilize any part of this memory? Are they allowed to access without any defined restriction? No, they should be ordered, right? Suppose you have one NUMA node environment. You initiated a query and it is passed on scheduler 1 and corresponding CPU. Of course, to run this query, we need memory for several objects. First, we need memory for worker thread, memory for caching, memory for query parsing, and different kind of objects depending on the query you are running. In SQL Server, we call these memory consumers as memory objects. However, memory objects itself cannot directly request memory. They should go through the next step, clerks. Imagine clerks as accountants, okay? They always record how much memory is being consumed by specific object. Clerks are divided into 4 types: general clerks, object store, cache store, and user store. General clerks, for example, include buffer pool clerk called memory clerk SQL buffer pool. Query plans also use memory, and they also have clerk called memory clerk SQL query plan. There are many other clerks available, the biggest one of course, buffer pool. Therefore, we always expect buffer pool clerk with the highest memory consumer. Next one is object store. Object store is a simple pool. It is used to cache homogeneous data. Sample object stores include object store service broker, object store LBSS, object store schema manager, and others. Cache store and user stores are just actual caches which have their own clerks and reserved memory, okay? I'm not going to dive deeper in this. What does this clerk mean in each clerk? Okay, you can just, if you want detailed description of each clerks, you can refer to Microsoft documentation, which is available online. Each of these clerks has a reserved memory in virtual memory. Okay, this is not allocated yet, but reserved. Each memory object is associated with clerks. For example, if SQL Manager object needs 2 MB to cache some data, it goes to cache store, register 2 MB memory there, and gets the memory. As a result, you'll be able to see 2 MB increased memory in clerk and object level. Here, I can say clerks are accountants. Objects should always register how much memory they are getting and for what purpose. For example, let's check our memory objects. You can check sysdm os memory objects command to find the names of the objects and how much each object has reserved and allocated. You can also check memory clerks with this sysdm os memory clerks command. Okay, let's run this command. This command shows that memory object called memObjectParse is using clerk called cacheStorePHDR to allocate memory. The allocated memory is nearly the same, as you can see. But one point is important. Memory objects and clerk relationship are not necessarily one-to-one relationship. One object can use several clerks, and they might not be object for some clerks. For example, SQL Server did not define specific object for buffer pool. Threads running on CPU directly contact buffer pool clerk without defining any object, okay, and consume memory. Therefore, do not expect the size of the clerks to be equal to the size of the objects. So, why do we need this? Why am I sharing you this information? I will show you. I have two VMs, SQL Server and client. We checked reserved and committed memory and found that SQL Server using a lot of memory, and it is constantly increasing. I can also verify the same with Task Manager. By looking at this, the first thing comes to my mind is what is causing this memory increase, right? For this, I quickly look at the clerk level information and find out that SQL buffer pool is consuming a lot of memory. This is okay because SQL Server utilizes buffer pool for keeping their query pages in memory, which is expected behavior, okay? So I do not touch anything. Then the next question comes, until where the buffer pool can expand. Can it take all the memory available? Let's now learn how memory consumption by SQL Server is maintained and cleaned if necessary. When SQL Server starts, it detects how much memory is available and it reserves the memory in this virtual memory. If there is not enough memory for reservation in virtual memory, SQL Server cannot start. We call this reserved memory as target memory or commit target, okay? SQL Server clerks cannot allocate more memory than this. This is the limit. Then clerks reserve and commit the initial sizes within this commit target. All these initial commits by clerks are summed and called as total server memory. You see this, for example, in Task Manager. This is a current SQL Server memory utilization, okay? So when SQL Server runs for a while, clerks start consuming and allocate more memory. As a result, total server memory starts to increase. For example, here, buffer pool clerk allocated a lot of memory, okay? This buffer pool will consequently stop at commit target level. It cannot grow more than that. Then, Resource Monitor, who checks memory consumption by clerks, initiates lazy writer thread and cleans this buffer pool. In this way, memory is cleaned from buffer pool and other general, please pay attention, general clerks. However, one important thing, there is difference between cleaning and releasing memory. When buffer pool is cleaned, it does not mean that SQL Server released memory. Once committed, okay, once allocated, SQL Server does not release memory. Therefore, although buffer pool is cleaned, total server memory and current memory consumption of SQL Server stays high, and the same. Okay? Let me show you. I initiated performance monitor and chose lazy writer, buffer pool clerk size, target server memory, and total server memory metrics. SQL Server just started, so my buffer pool is empty. Let me fill this buffer pool by simply running this select query. This table is huge in size, and running this should bring a lot of pages from disk to memory, right? So execution starts. Let's see the buffer pool grows over time. As you can see, buffer pool size is increasing, which is causing total server memory also to increase. You can see here also with tsql committed size. This committed size is reflecting that increase in total server memory. In other words, this committed KB is equal to total server memory, and this committed target KB is equal to target server memory. Let's see what happens if buffer pool reaches the limit. Okay, the limit is, as you can see, target server memory. By the way, we can also see this increasing size in task manager. We reached the limit, and we can see that lazy writer just started and cleaned buffer pool. Bingo. As a result, buffer pool size decreased. But did it SQL Server release memory? No, right? As you can see, total memory size is standing the same. Okay, and it is not decreasing or increasing, because it cannot increase because we reached already limit. It cannot decrease because we did not release. Okay, we can also see the committed size is standing the same in task manager also. This all what I talked about until now, and you should know. Okay, by the way, if you want to manually clean buffer, we can run this clean buffer dbcc command. As you can see, it cleaned buffer. So to summarize, clerk size over time increases. Okay, but we will clean this clerk size by initiating lazy writer. But although lazy writer cleans the buffer pool, it does not release the committed memory. Okay, we talked about general clerks and buffer pool, right? Lazy writer can help only in the case of general clerks. What about other type of clerks like cache store, user store, object store, right? Do we use lazy writer here also? No. How these cache are cleaned when they consume a lot of memory like buffer pool is a little bit different. Okay, let's see. We have this target memory and total server memory as before. Suddenly, due to some client activities, cache store became big and started to consume nearly all commit memory of SQL Server. At the time, Resource Monitor detects this memory contention and starts to decrease the cache. How does it do? It uses clock system. Let me show you how this clock system works. Suppose you have this amount of cache and you have 10 data objects in this cache. When these objects were created, values are assigned to them. For example, like this. The more the object is used and the newer the object is, the bigger the value it has. For example, here, the first object has the biggest value, indicating this object is being used often by SQL Server, or this object is very much new. When there is a memory pressure, Resource Monitor starts clock system. This clock system then goes through the objects and subtracts one from each object in one runtime. Then the objects with zero values are removed from cache. If there is still memory pressure, clock system runs again and does the same operation. This process continues until the memory contention is resolved, and in this way the object store, user store, and cache store are cleaned. So, if we summarize what we learned until now, there is a target server memory, total server memory. If any clerk consumes a lot of memory within this commit target, Resource Monitor cleans it. For general clerks, we use lazy writer, and for other type of caches, we use clock system. This type of memory contention is called as internal contention. Before finishing this session, I want to talk about external contention and paging out issues also, which you might often face, okay? We say that when SQL Server is started, each clerk reserves and allocates initial sizes, right? At the time, the sizes are allocated in physical memory. We call this part as working set. Then, as you know, after running for a while, SQL Server starts to utilize memory within its commit target. Let's say buffer pool increased a lot, but not so much. We are not experiencing internal contention yet, as we have still enough space until limit. At that time, since we have a physical memory available, all this increased buffer is located inside the physical memory. As a result, our working set increased a lot. Now suppose another application starts in your server and wants a lot of physical memory. In this time, OS experiences physical memory contention. We call this type of memory contention as external, and it comes from Windows OS. At this time, what does Windows OS do? In this case, Windows does page out operation by moving out some SQL Server data to the disk. This is a hard page out issue. In this way, Windows OS tries to resolve memory contention. If there is still memory contention issue, OS will continue paging out and move a lot of data to the disk. This actually causes performance issue in SQL Server, because if SQL Server wants to use any of this paged out data, Windows OS should page in to the physical memory and hand over to SQL Server. This is very much time consuming, and your queries as a result faces latency. Therefore, SQL Server logs this kind of paging out issue every time it occurs significantly. As you can see, my whole data is around this 25 GB, but only around 10 GB data is located as working set in physical memory. Remaining 59% is located as page file on disk. So, this is considered as a serious paging out issue. SQL Server is reporting it. So, what should we do to prevent paging out issue? First of all, you should always start by investigating who is consuming this much memory and causing memory pressure. Also, you can configure max server memory setting. In this way, SQL Server will commit less memory and less page out will happen. You can also configure log pages in memory. In this case, Windows does not page out SQL Server memory pages. Okay? So, I tried to cover important concepts in this session as much as possible. Of course, I cannot cover all of the things, but I hope that you found this useful. Please do not forget to like this video if you found this information useful, and follow for more interesting sessions about SQL Server. Thank you for your time.